within this next section, I think it can be very kind of confusing at all the interconnecting pieces, and everything looks different. I've changed how I've presented the material to try and point out the common features between everything. Okay, so we don't look as much at the specific reactions, because what we're going to try and do is look at what makes them common so that you can apply that common logic to all of them as opposed to memorizing each one individually. Okay? But there are a lot of reactions. What this next section deals with is our addition reactions, and in particular our electrophilic addition reactions. Because we're running an addition reaction, what needs to happen? Something needs to be added. What is that something being added to? Okay. And we called it an electrophilic addition. And really it should be an electrophile addition, which means we're adding an E+. So what must we be starting with? What reacts with a positive? A negative. We need to be starting with electrons. Okay. If those electrons were, say, on an atom, let's just call it A for atom, what kind of reaction have we done?
Coordination.
We've done a coordination, okay, which we would see in which type of reaction? As a hint, it's not addition.
Substitution?
It would be a substitution. The whole point is that we're doing an addition. And in addition, what are you reacting? What must happen in an addition reaction? You must break a pi bond. Okay, so we're starting with a pi bond. That pi bond reacts with the electrophile to then be added to the structure. Okay? In the process of doing so, we took electrons from the pi bond, shared them with the electrophile. There's our new sigma bond. What happened to the other carbon? Okay. At this point, it would be left as a carbocation. So that's kind of a repercussion of the electrophile addition. Depending on the reaction conditions, that carbocation might exist, it might not. Okay. So what we have to do is evaluate carefully those reaction conditions. Before we get into those reaction types, though, we need to recognize what we're starting with. We're starting with a pi bond. We're starting with alkenes. Okay? Which is why most textbooks, when they introduce this, say we're now talking about alkene functionality, and they go through and make some comparisons about alkenes to the previous functional groups we've looked at. Okay? So if we go back and look at it, our intermolecular forces for alkenes tend to be strong LDF forces. Why not just LDF forces? Why should we call them as strong? What do you got, David?
They have an easily polarizable pi bond.
That pi bond is polarizable. That's what makes it reactive. Because it is polarizable, that increases the strength of the interaction between the molecules. Okay? It is very heavily structurally dependent on melting point and boiling point. When we go through and look at, say, alkyl halides or even alcohols, we care less about the structure. Why? They have stronger intermolecular forces, so those dictate our melting points and boiling points. Because we have a relatively weak intermolecular force, structure can have a big play in this. Okay? Once we're looking at pi bonds, where we would be referencing cis versus trans conformers, changing how your melting point stacks out. Okay? The next big thing would be the reactivity of that particular functional group. When we look at a pi bond, they are all carbons and hydrogens. So we're looking at nonpolar covalent bonds. None of these would be very high up on that reactivity predictability. Okay? So we might say, well, how could I get them to react? Well, we already called attention to it. We have that pi bond. Okay? That pi bond is a source of electrons. It can act as nothing else. It can only act as a source of electrons. Because it is a source of electrons, when we look at the alkene, we have a nucleophilic carbon because it can donate electrons. What could it donate electrons to? An electrophile, in which case it's a nucleophilic carbon. What else could it donate electrons to? An acid, in which case it's a base. So when we're looking at alkenes as a functional group class, all we're really trying to say is that a pi bond can either act as a nucleophile or a base. Okay? Because those are distinctly different chemical reactions, one's acid-base, one's electrophilic addition, okay? We divide those into separate categories to talk about them. The acid-base category is chapter 11. I think it's 11. The electrophile addition chapter is chapter 12, and then bits and pieces in chapter 25. Right? I think it's 25. So what we're trying to see is find those commonalities behind their reactivity. Ultimately, the very first thing that needs to happen is the electrons of the pi bond must react. Okay? If we go through and look at some structural features, all of the carbons, or the carbons of the pi bond, will be sp2 hybridized. We have the p orbitals above and below the plane. Interesting, if they're above and below the plane, where do the electrons leave the structure? From the top or from the bottom? Either, which means how many products? 2 products. Okay? So just like our SN1 or our E1, additions are going to be problematic with the amount of products we get. Okay? We almost universally will get 2 products. Okay? Or 2 potential products is the best way to phrase it. Because we now have a degree of unsaturation, it's a good point to review back that we have degrees of unsaturation that we talked about back in Unit 2 when we looked at mass spec. There's fancy formulas that you could go through to calculate 2 times number of carbons plus 2 plus nitrogen minus halogens minus hydrogen divided by 2. Gets you degrees of unsaturation. Meh. I would argue that's not that big of a deal. It can be useful. I've just never found it worth my while to really memorize that formula. Okay? Ultimately, the part that does matter is 1 degree of unsaturation is equal to a pi bond or a ring. Okay? So pi bonds and rings have pretty much tied chemistries or tied end results. This is why we could do cis and trans with a pi bond and why we can do cis and trans with a ring. Okay? We get the same effects. Okay. Cis-trans isomerism. We had a little nomenclature video on it that some people look like watched and some people may have missed. So let's real quickly go through our cis-trans rules. Cis and trans don't work all that well. They aren't a nomenclature system. They just say the relative location of 2 groups. Those 2 groups could be anything. Okay? So not nomenclature. Z and E is our nomenclature system. So we take a pi bond. Let's do a carbon. Let's do let's do that. And that's a lie. I'm going to make some adjustments here. Simplify that one down to just the CH2. And bad idea to do the OH. When assigning our priorities with pi bonds, the first thing to do is to cut it in half perpendicular. Okay, so it's now cut in half. And I want to look at each of those halves and look at the pieces connected and assign priorities. So if we look at the left half, which is a higher priority?
Bottom.
Top or bottom? The bottom, because?
Once you go up far enough, you hit hydrogen on the top and carbon on the bottom.
Carbon, carbon. Then the rest are hydrogens, so there's no difference there. Then we go to carbon, carbon. 2 hydrogens plus 1 hydrogen. Where's our difference? The bottom one goes out to a carbon versus a hydrogen, which is a higher priority. Carbon, which means the bottom gets starred. Now we can move to the right half of the structure. which should look suspiciously familiar. In fact, if you were paying attention, I believe it is question 1 on exam 3. And it was question like 5 or 6 on exam 2. And on exam 2, 100% of the class got it wrong. On exam 3, it was about 80% of the class. Remember how we say we should go back and review our exams? This would be a good reason to do so. Right? Which is higher priority? Top or bottom? So, our rule, we go out to the atom. First atom we encounter would be carbon versus carbon. Is there a difference? No. So we go out again. We see a hydrogen. We see a hydrogen. There wasn't a difference. So what do? We can go out to a carbon. We can go out to a carbon. Still no difference. Top one we go out to a carbon. The bottom one we go out to a hydrogen. Which has a higher priority? Carbon, which means the top is the highest priority. I don't care that bromine is on the structure somewhere. I don't achieve the difference in those two structures, or I achieve the difference between those two structures well before I get to the bromine. Okay? This is one of the biggest misconceptions when dealing with RNS. It is an atomic comparison, atom by atom. When you find that first difference, that's when the difference comes out. Okay? Not when I go, oh, there's a bigger piece out there. I don't care that it's bigger. I'm looking for that first difference. Okay? Now that we've got our stars, we can cut it in half parallel to the pi bond. Where are the stars located? Opposite of that line, which then means not trans, E. Okay? And why not trans? Trans specifically only refers to two groups. How many non-hydrogen groups are on that alkene? 4, not 2. So I can't evaluate that as a cis-trans double bond. I need to use the EZ nomenclature. Okay? Just to give you an idea, this we said was trans, right? What is the relationship between the CH2 bromine and the propyl? I want to know the relationship between these two circles. Where are they?
Same side.
On the same side, so they would be?
E. Oh, Z.
Cis. They're on the same side. Okay, I would not use E and Z. E and Z is a nomenclature system. I'm not talking about naming it. I'm saying what is the relationship between those two pieces. Okay? If I want to know the relationship between me and no one in here is Kevin, that works. He's my brother. That doesn't mean, hey brother, his name is still Kevin. Okay? But the relationship that he and I have are brothers. We can identify that relationship. Cis-trans is a relationship. E and Z is nomenclature. Right? Sometimes they blend, okay, or they blur. Because if I went up and said, hey bro, he's probably going to respond, okay, even though I didn't call him by his name. Make sense? Okay. All those nomenclature rules still apply. Okay, so you still got to deal with all those pieces. Do you have them memorized yet? I wasn't saying because you just looked at it this second. I was saying because you've seen this slide now 4 or 5 times throughout the semester. Like that should be committed to memory. Ballpark. Okay? If you're in the ballpark range, you're probably good. Okay? If that looks foreign to you, you're going to bomb virtually every nomenclature question on the exam. Okay? Which is kind of up to you, but realize there's lots of other sections that you probably also didn't want to pay attention to, like spectroscopy, like chirality. Those require a lot more practice and skill to deal with the nomenclature. Okay? So, which ones do you want to do?
why not all of them?
Because I don't want to do all of them.
Please. Then let's do the second one.
Second one? That's nice. Appreciate that one.
You're welcome.
Any other thoughts? Okay, we'll throw this one in there too. So, together or on your own?
Together.
Together? Okay. So let's look at the top one first. What's the first thing we should do?
Look at the highest priority substituent.
Okay. We want to find the longest carbon chain that contains the highest priority substituent. The pi bond is a very high priority substituent. Okay? So we could probably already identify that those carbons need to be part of the backbone. Okay? And if we look to the left, well, there's a carbon, the bottom one is a chlorine, so for the sure to the left, we have to go up. How about to the right? Should we go up or down? Up, because there's more carbons, which isn't a bad conclusion, except that it is wrong. The OH is the highest priority functional group, which means it has to be in the backbone of the chain. Right? Has to be included. Which means my longest carbon chain is 4, and I end up with bute for 4. Do I have any hybridization considerations? Like, I don't know, like a pi bond? Yeah. Yes. So in that hybridization consideration, I need to say ene. Where is that alkene located? Carbon 2, between 2 and 3. Okay, we always assign the lower number, so it's going to be a 2 ene. Do I have another high priority functional group? I have the alcohol, which will be all. Okay. Where is it located? Okay. The big answer that most people do is drop in a 4. Because if we count 1, 2, 3, 4, and it would absolutely be at position 4, except alcohols are the highest priority functional group, which means it has to be 1. Right? By circling the main chain, I can now identify that I have substituents. Let's look at the left side of the structure. What are those substituents called? These are chloros. Okay, how many chloros do I have? 2. So it would be dichloro. Where were they located? Position 3 and 4. This is why we number, so we don't get confused and start calling them 1 and 2. Okay? Drop the numbers in there for a reason. All of that work should be showing up. Upper right-hand corner. Okay. Interesting. You decided to call that an ethyl because you saw 2 carbons, right? Isn't there a third carbon? So we hear some people saying, well, shouldn't that be a propyl, not an ethyl? No, it should not be a propyl at all. Propyl is actually going to be sort of wrong in this case, depending on how you want to break that down. Okay. The official way to name this, you are correct, it is an ethyl. Okay. But does that account for all of the pieces? No, it's missing that methyl on the ethyl. So we would call this methyl ethyl. Where's the methyl group connected to the ethyl?
On carbon 1.
Why is it carbon 1?
Because the ethyl is that C is the 1.
Okay. For substituents, our nomenclature numbering starts where it connects to the main chain. Okay. That's the rules. That's 1, 2. Which means the methyl is located at position 1, and I would get a 1-methyl ethyl. Where is the 1-methyl ethyl located?
Carbon 2.
At carbon 2. So this is 21 no. 2 what?
Oh.
And we can drop the parentheses around it, and now it becomes a little bit clearer. Those parentheses are things that you should include. Why? If we drop the parentheses, it can become confusing. Okay, but that's pretty much it. How do we put the name all together? Alphabetically, starting with chlorine over, I believe it is over ethyl. Okay, and I could be wrong on that, but I'm pretty sure that's the case. Okay, either way, chlorine's going to beat out ethyl or methyl. So in this case, it didn't really matter. But chlorine trumps the ethyl and the methyl, and so we would get 3,4-dichloro 2, 1-methyl ethyl but 2-ene 1-ol. Okay, that is the full IUPAC name, okay, in full sequence. Is there another name that you could give to that substituent?
Yes.
Yes, there would be the common name, which would be 2-isopropyl. Officially, allegedly, you are not responsible for common names. I kind of find that to be a load of BS. Right? For the most part, it plays a very minor role. Common names sneak in kind of under the radar almost by accident. Right? They do seem to do a pretty good job of keeping the common names out and sticking with IUPAC. Okay? Kind of makes sense? Okay. Final sequencing. We'll start with A, then B, then C. Bottom one. Actually, no. Screwed up. What's wrong with that name?
We don't have E and Z in it?
If we go through and look at our structure, we do have E and Z possibilities in that. Okay. With all of the drawing on there, it might be nice if we had a way to clear it all away. On the ACS, you will have a way to clear it all away because I will give you tracing paper. And what do you now need to do? Slide the tracing paper over. Now all of that work you don't have to erase or think about or overlay on top of. You've got a fresh canvas to now write your work down on it. Okay. For those of you right now, all you could really do is erase or redraw everything. For me, I'm going to go through and erase as long as you okay it. That might have been selective hearing. So, step 1.
Draw a line through the center
Perpendicular to the pi bond. Look at each half. Chlorine versus carbon. Chlorine is a higher priority. Carbon versus carbon. Okay. Hydrogen, and then we go out to carbon versus oxygen. We do have a difference there. Okay. In this case, our oxygen's going to win out. There's our star. We cut parallel to the pi bond. Where are the stars? Same side, which means Z. So first, in front of our whole name, what do we get? Z. Where's the Z located? Carbon number 2. 2Z, 3,4-dichloro, 2, 1-methyl ethyl, but 2-ene 1-ol. Yay! Gotta love it. Okay. Bottom one. How many carbons? 6. So we've got a hex. Okay, how many double bonds? 2. So a hex di. Diene. Where are the double bonds located? 2 and 4. So a hex 2,4-diene. And I can never remember if you need that A or not. But if you're going to tell me that you need the A, then I'm going to say okay. Yeah, I'll just accept that. They don't test that. That's why I like multiple choice. Okay. Would our name now be correct?
No.
No, what's wrong with it?
We're missing Z.
We're missing the E and Z. Okay, well, since the double bonds are the same, it's not really going to matter. It's just going to be ZZ, right? What was it, 2, 4?
Whoa, isn't it? 2?
Whoa, Okay. What's the whoa?
You've got one E and one Z.
That first one, they're on opposite sides. So that would be E. That other one, they're on same side, so that would be Z. So how do I put the name together?
Z goes first.
Is this 2E4Z or 2Z4E?
2Z, 4E.
Nomenclature says there's only one correct way. Right? This was an accidental question because I just put it together just kind of for the sake of it, and then somebody asked that smart aleck question, which one comes first? I was like, I have no freaking clue. So it took a little while, but I did some digging. Rule 2.2.3, Z over E, which means it needs to be 2Z4E. Why does Z come before E? Because F the alphabet.
I remember that from the tutoring center. There are a lot of unhappy people about that.
Yeah. Okay. And for the record, this isn't just like, sub-point 2, sub-point 3. This was an addendum to the book. Okay. So you're looking at several tiers of rules to get through before you finally see the difference between Z and E. Why does Z come before E? Because somebody said so. That is nomenclature. All of nomenclature is because somebody said so. Okay? It didn't just come from nothing and like, oh yeah, everything makes perfect sense. Someone just said that's the way it works. Okay? The very thin argument in my mind, Z and E ultimately come from cis and trans. Z is on the same side, like cis, and cis begins with C, and trans begins with T, so yeah, pretty much. I mean, with only two things there, I'm just making stuff up to make it work. That's about all I got. Okay? Welcome to nomenclature. Okay. So, alkene addition. Okay. A lot of people like to refer to these as wheels of death. Probably not far off. I like to refer to them as spider diagrams. Okay. These spider diagrams pick a particular central structure, and then we run reactions off of them. All of these reactions you are responsible for. Just because of that, there's the deep sigh, and those, and those. And I'm missing some. Okay? So one of the things that can become daunting is you look at this and you go, oh my God, there's so many different things. What you need to be looking for is not the differences, but the commonalities between them. If you can identify those commonalities, you can categorize and group things into memorization pockets that you can then answer the questions better. Otherwise, yes, it sucks. You have a lot of memorization to do. Okay? So, when we go through and look at this, the structure was picked very carefully. You'll notice this isn't just a standard alkene. Okay? This is an asymmetric alkene. Why? What happens with some of our products? What do we see? We see chirality. We see asymmetry in those products. If the starting material did not show that asymmetry, we would not see that asymmetry in our products. Okay? So the starting structure for most spider diagrams involves a lot more information than is directly obvious about. Okay? So you could be asked a question that is vastly simpler than what's shown up here. Okay? Part of what you're trying to do is to recognize the patterns on why those things are happening. Kind of make sense? Okay. So, let's see if we can real quickly come up with some common patterns. H plus would be what reagent class? Acid. H3O plus. Acid. HX. Bless you. Let's not circle that one. Cool. All three of those do what? They accept a proton, and then they accept electrons from what? Whatever the other species was. Look at the products. They're all effectively identical. The hydrogen goes to the same place, and whatever that other piece was goes in at the other location. Where did the other piece go? Our OR, our OH, and our X. They all went to which position? What can you tell me is special about that position versus that position? Whoa. Yeah.
That's the one with the methyl.
Okay, we could go with that. That's the one with the methyl. Okay, why would that matter? The red position is more substituted. The blue position is less substituted. Okay? So a red position, more substituted. What things might be more stable if they were more substituted? A carbocation. What do you think might be happening as an intermediate in all three of those?
Carbocation.
Guess what forms? Carbocation. Okay? So if we can look for those similarities and patterns, we could start to make some predictions about reactivity. Okay? Just because I noticed it and I can point it out, if we continue around that wheel to the right, we need to include the hydrogens being added, but on the same side. Why would those hydrogens get added on the same side from our H2? How big is a hydrogen?
Pretty small.
Pretty small. Would two hydrogens be able to span the distance between two carbons? Probably not. Right? So why would I need the hydrogens to go in on the same side as opposed to opposite sides?
Because they're closer physically in space.
Closer physically in space. If I broke one of those hydrogens off, the other one's floating around, right? Right? In that floating around, would it be particularly stable? No. What's it going to do? React with the most reactive thing is it can find. Guess where the most reactive thing is going to be as soon as it breaks off? Immediately next to it. Okay? I won't identify what the charge is on that immediate next to it, but that immediate proximity is going to drop that hydrogen on there. So if we can think about size, that can have an impact. Okay? If we look at the bromine, Br2, similar thing, diatomic element. The bromines are added on opposite sides. Why would the bromines all of a sudden be added on opposite sides as opposed to same side? Hydrogen's added on the same side. What's the difference between hydrogen and bromine? Someone else? Size. So if the bromide broke off, could bromide stabilize that charge? Yeah, so what happens? It floats off and chills on its own, which then gives it time to potentially come in from the backside. The other bromine was so large that it prevents the second bromine from immediately reacting. Okay? So if we take into consideration these size effects that we've talked about and hybridization effects, we can start to come up with explanations for each of these reactions. And that's ultimately what this next sequence of material is trying to go through and do. Okay? If we look at these reactions, chapter 8 is pretty much right here. Chapter 10. Chapter 11 is, I believe, all of these guys. Chapter 25 is this guy. Right? Actually, I think both of these show up in chapter 25. Could be wrong on that. Okay? So what we're looking for is that Carty, when he went through and looked at this, saw some differences in those relationships, try to categorize them a little bit differently than most textbooks. Okay? So what we're trying to do is say, well, why did he see those commonalities? Right? And try and group and come up with explanations for those. David? You had a hand?
Yeah, I was wondering why 25, why that's so far off.
Why in sequence? I don't know why he put it so far out in sequence. Okay. That's something I haven't talked to him about. Right. Alkene oxidation. Right. And I'm now pretty sure 25 isn't that one, but in any case, I'm getting my chapters confused. Alkene oxidation reactions. Okay? So now we're reacting the pi bond, but we're reacting the pi bond to specifically do what? Oxidation reactions. How do we know those are all oxidation reactions? Lots of oxygen. Where did the term oxidation come from in the world? Why did we use oxidation? It was literally because when we first observed it, it was the reaction that happened when exposed to air and ultimately oxygen in the air. So if we increase bonds to oxygen, we've done an oxidation. All of these are examples of oxidation. Okay? We will also have to deal with the reductions. Okay? Within the reductions, we've already saw some of this on the previous slide, but we'll see that reduction show up as well. Notice the bottom one gets a little bit trickier. Why does the bottom one get trickier? What is special about that pi bond? There's two pi bonds, which means?
Linear.
Yes, it's linear. What would happen if you had two pi bonds? Alkenes can react with what? What are alkenes reacting with? What makes them reactive? The pi bond. What's special about an alkyne? It has two pi bonds, which means not necessarily more reactive. It can react twice. It has two pi bonds. Okay? So virtually all of the reactions shown up in the slides, you can now switch out and put in an alkyne, and guess what happens? The exact same thing. It can now just happen twice instead of once. Okay? The chemistry is almost identical because it's still a carbon-carbon pi bond. Okay? So if we focus on the commonalities between those, we can get through the chemistry a little bit faster. When we encounter weird things, say like, why the hell did it stop at an alkene? Well, those might be things that are more relevant to memorize. Like hydrogen gas in the presence of Lindlar's catalyst does something bizarre. It doesn't react twice, it reacts once. That might be something that's worth committing to memory because that runs counter to what we would expect. We would expect it to react twice. It didn't. Memorize. Okay? On top of which, what else would be interesting about that reaction?
Cause a
What can you describe about that pi bond? It's a cis pi bond. And what do we know about cis pi bonds?
higher energy.
They're higher in energy. There's another reason that we should probably memorize that because that's not only just doing one pi bond reaction and stopping, it's forming the highest energy of those. Why might we memorize the bottom one? It also reacts only once, but it forms the opposite. Right? So those two reactions are now running kind of counter to anything that we might memorize or have seen in commonalities in other places, which means we should probably memorize those reactions because those will probably get tested on. Okay? Make sense? Okay. So that's our big overarching summary. Okay? You should be spending time to memorize those diagrams. Okay? When? Now. Okay? Come Wednesday, you should have some aspect of those three slides memorized already. Because what we're going to be doing is then talking about how and why those things happen. If you already know the what, you've simplified the amount of work you've got. Right? Memorization is just looking at stuff. Start looking at it. So, our addition reactions. 24, it wasn't 25. Right? So our electrophilic addition reactions, or electrophile addition reactions. All of these involve a nucleophilic, nonpolar pi bond. Okay, why must it be nucleophilic? Because a pi bond literally has electrons. It shouldn't act as an electrophile because it has electrons. Right? So it is now nucleophilic. So if we're looking at the electrophile addition reactions, we're taking a pi bond, and the pi bond is breaking because it is leaving to react with an electrophilic atom. Okay? That results in the loss of the original pi bond. Okay? There are all sorts of other kind of side issues that can pop up with this. Okay? So the first and foremost thing to address is that if that nucleophilic atom, our electron source, shares electrons with acids, we're looking at chapter 11. Okay? And so now we look at all the basics of acid-base reactions with nonpolar pi bonds. If it shares electrons with something other than hydrogen, well, now we're looking at standard electrophiles. We have a new chapter, or chapters ultimately, chapter 12 and chapter 24. Okay? That's going to cause a shift in how the reactions overall potentially happen. Okay? That said, let's go through and take a look at the general reactions shown. Our pi bond acts as a nucleophile and reacts with what in that first reaction? Sorry, a base reacts with the hydrogen. What charge was the hydrogen? Okay. If we look at the second reaction, our pi bond acts as an electron source and reacts with the electrophile, which is what charge? So it's doing the same chemistry? Really? That would exceed the octet and shuttle electrons to the nucleophile. Right? Which would mean that nucleophile is partially... What happens on the other side? Hydrogen would exceed its octet, so it shuttles its electrons to the nucleophile, making that species partially negative. Right? Can a pi bond react? Like, if I drew the product, does it make sense to just have that hydrogen floating out of the middle of the bond? No, the hydrogen's specifically connected to one of those carbons. Notice that in both cases, where's the hydrogen connected? Hydrogen versus the electrophile are both connected where? The least substituted position. I wonder why that is. Why would the least substituted position be most likely to react with a positive? Because the negative, so I'm hearing carbocation, we want to take a step back and away from, because it's not the carbocation that's reacting. What's reacting? The pi bond, in particular, the electrons on the pi bond. So I don't want to be thinking necessarily about a carbocation. I want to be thinking about a carbanion. Okay, a carbanion. Okay, where would I expect the electrons in that pi bond to congregate? Why should they congregate to the right side? So you're saying that we should do something like this. What did you just suggest I do? What is the relationship between that black structure and the starting alkene? Resonance? Yeah, you mean resonance can tell me why and how this reacts? Yes, abso-freaking-lutely. Okay? It is that resonance structure that dictates that you put the negative charge there and your positive charge on the inside, which then means when I go to react with the partially positive hydrogen and the partially negative nucleophile, where should the charges align? Positive to?
Negative.
Negative. Negative to? Positive. What happened on the other side? Negative to?
Positive.
Positive. Negative to?
Positive.
Positive. It exactly matches. One of the most frustrating things I see within the electrophilic addition is that people have this tendency to go through and saying, well, it's doing the opposite of what I would expect. No, none of the reactions do the opposite of what we would expect. They all do exactly what we would expect if we have any concept of electrons and protons. Okay? That concept is very often buried in resonance, which is why resonance is so important. You have to be thinking about those resonance structures. Okay? For those of you that think that's too hard, that is okay. Welcome to memorization. Okay? That is your only other out. You don't have an option. You either apply or you memorize. Okay? So, let's take a look at that nucleophilic nonpolar pi bond. Consider the balance of the structure via resonance. If we look at that starting structure, it is reactive because of those p orbitals. Right? And those electrons are being shuttled back and forth between those two positions. If we evaluate all of our resonance options, we could draw the option where we have the negative charge on the inside, or we could draw it where we have the negative charge on the outside. Make sense? Which of those options is better? The blue one in this, God, I hope I didn't screw that up. Oh, I did. Did I didn't? No, I didn't. The blue one is better because I'm putting negative charge on the least substituted position. Okay, that makes that negative carbon the most stable. By that same token, the carbocation is also now placed at the most stable position, which makes it more stable. All right? That small bit of information now allows me to be able to predict how this alkene will react in its environment. Because when I throw in other charges, I know those charges are going to align to neutralize around the blue structure, not the red structure, because the red structure isn't as stable. This is looking at your first worst resonance. Exactly what I told you at the beginning of the semester. Yes?
Is it possible to interact with the red structure? Does that ever occur?
It is always possible to force something to happen, right? So looking at how I can possibly do it. It is possible that my hand can be aimed backwards behind me, right? That my right hand could be connected to the left side of my shoulder. It is possible. Yes.
But I mean, like,
Do I want to do that?
No.
No. So don't start trying to extrapolate out to possibilities if you don't have to.
I was just wondering, like, we had some of the other ones with like trans and stuff, where you can get cis and trans products in the same.
So, and that's an interesting idea to try and throw back and say, well, but we had cases where we had opposites. Why did you have those cases?
Because they're attached to either side.
Not in the case of the cis-trans option. The electronics were only allowed to form in that way. The electronics only allow you to form in the blue way. Okay? So we have not encountered weird exceptions like that. There's very logical explanations for why those shifts happen the way they happen. Okay? The only way you'd be seeing the other one react is if you brought in some other kind of system to evaluate. Don't bring in a fictitious thing if you don't need to. Okay? So, what does this set us up with? Okay? Our alkene is a weak nucleophile. I do have that negative, but it's not formally negative because I got that positive right next door. Okay? So I'm using the resonance to help me predict the reactivity. That does not make this a strong nucleophile. Which means to get it to react, what do I need to react it with? A strong electrophile. I'm going to need something to force it to react. This is why we have to use strong acids to force the reaction to occur. This is why when we move into chapter 12, we have to use strong electrophiles to force it to occur, to force it to react. Okay? So, if we look at our pi bond as a base, what happens? We take an acid. The most reactive thing in that case. So let's clean this up. What is the most reactive thing?
H+.
Does everybody agree? What did we just spend half an hour talking about? The pi bond. What's the most reactive thing? Yes, that was me being leading. What is the most reactive thing? The acid. All right? That acid is reactive because it's a strong acid. That is H+. Because that is a strong acid, what do I need to find? A negative. Where's there a negative? The electrons in the pi bond can now be forced to go out and react. All right? Where should that hydrogen connect? Okay. The best way to figure that out would be to draw a resonance structure. So we can draw it out, and clearly we would see that the left resonance is better than the right resonance. Right? This one is by far better than this one over here.
No, I don't see that.
And you don't see that? Yeah, they're the same. Is there an asymmetry to the molecule? No. Does it matter where we attach the hydrogen? No. There's symmetry. I don't have to deal with it. Okay? So don't always be like, oh, I have to super stress on it. Look at your molecule and decide, is there a symmetry with it or not? Okay? Since there is symmetry, it doesn't matter where I place the hydrogen. Once that has happened, I've done an acid-base step. An electrophilic addition reaction. Okay, because we broke the pi bond. This results in the formation of a carbocation. The carbocation is not stable, so what happens? Our A minus, our conjugate base, comes in and attacks to stabilize, and we get our final structure. Okay? The overall reaction is an addition. Okay? And in fact, I'm labeling that top one incorrectly. That is not an acid-base step. That is an electrophile addition. Why is it an electrophile addition? We broke a pi bond. It has to be an addition.
Oh, okay.
Right? In the process of it doing that, we also transferred a hydrogen. Acid-base reactions are only the transfer of a hydrogen. Right? Should we have done the coordination and that electrophilic addition at the same time? What was the most reactive thing? H plus. Right? Because that is my sole site of reactivity. The conjugate base, by definition, is stable. There's no reason for it to react immediately. I form the carbocation. Once I have the carbocation, the conjugate base can come in and act as a nucleophile. Okay? When we go through and look at this, we have to decide something about structure and mechanism. Okay? The structure and mechanism is what's going to force the stereochemistry and the regiochemistry. The regiochemistry is where did the hydrogen go versus the conjugate base, hydrogen versus nucleophile. In this case, did it matter? No, so regiochemistry was irrelevant. Why did it not matter? It was a symmetric molecule, so I don't care necessarily where the hydrogen and the conjugate base go. Do I care about stereochemistry? In this particular reaction?
Yes.
Okay. We've got a CH3, an A, a CH2, and an H. What do we have right there? That is a chiral atom. Do I need to be concerned about stereochemistry? Yes. Yes, I absolutely do. Do I have to be concerned about stereochemistry twice?
No.
No. Why is that other position not stereochemistry significant?
You have a CH3, a CH2, and then
Two hydrogens being the same, I don't have to worry about chirality there. What kind of chirality would I expect in this product? Okay. Would this product be optically active?
no.
Okay. It is not optically active. But I have a chiral product.
Yes. You have a racemic mix.
What do you mean a racemic
I
mix?
have a 50-50 R and
How did I get 50-50? I only see two things, or one thing shown there.
you have a pi bond. So can you draw it like sideways looking down the carbon chain?
Pi bond's irrelevant.
Sorry, not a pi bond, p orbital. Right there.
See that carbocation? That carbocation is a p orbital coming in and out of the plane, which means where can the nucleophile attack?
Either side.
From the top or from the bottom. I get two products happening right there. Okay? We are right in mentioning that the pi bond is important, and the pi bond can react from two sides. Does it matter in this case? Why not?
Because it's symmetrical.
Not really. And yes, it's symmetrical. That's not why I'm saying not really. For me to worry about it, what would have to be a result of the loss of the pi bond? Said the other way, the last step, I had to worry about it. Why did I have to worry about chirality for the last step?
That's when we got a chiral atom.
That's when I got a chiral atom. When do I need to worry about the pi bond and how it reacts with chirality? When the result of the pi bond formation results in a chiral atom. Did it result in a chiral atom? No. How could it have resulted in a chiral atom?
If that wasn't, okay, yeah.
Now in that first step, what happens? That's not a CH2, or an H, that's a CH2, CH3. Is that where that hydrogen connected a chiral atom now?
Yeah.
It is, because that's a carbocation, which was kind of an unintentional effect. Right? That is a chiral atom, so now I would have to be concerned about how the pi bond reacted. Right? This becomes very careful at each stage evaluating what is reacting and how it is reacting. It isn't just as simple as electrons move out, but it's where are those electrons moving from and towards. Right? Those are all those little layers that go into it. How often do you need to worry about that? Maybe 10% of the time. Right? Is it something you need to at least be aware of and cognizant of? Yes, because I want you to get 100%.
It'll still be receiving though, right? Because when you get that negative, it jumps into a p orbital.
We'll actually see it in a little bit, I think. So,
I think like one might be slightly favored over the other.
yeah, you'll still end up with each of those reactions would be racemic, and you get a giant mess of products at the end, and we'll look at that. All right? So what would happen in an energy diagram?
You have something medium high.
Right? If we start with an energy diagram, what's going to be the first thing we would want to do? Do I have a thing? Look at a mechanism. Okay, so we've got three things, starting with reactant. Where should our reactant be?
2/3 up the chart.
Okay. I would argue you should always put your reactant right in the middle. You don't know where you're going. Ultimately, it doesn't really matter. You can place it wherever you want. Where should your intermediate be?
High energy.
Why should it be higher in energy? Because there's a carbocation. Where should your product be? Lower than what?
Both.
Then both the reactant and the intermediate, because
Because all sigma bonds is lower energy.
all sigma is lower in energy than a pi. So there's my product. I can now go through and do my energy diagram. The most important step is going to be that very first step. Okay? So I'm concerned about that electrophilic addition. What causes that to happen first? Kind of makes sense? Yes.
This is a second step, a second order mechanism?
Yes.
Okay.
So if we looked at a rate law, this would be a second order because it requires the alkene and the acid in it.
Do we name those like we did with SN1?
Nope, we don't have to worry about it. Okay.
Are all additions going to be at least second?
Yes.
Okay.
Yes. What happens if you have an unsymmetrical alkene? Okay. What do we have in common in each of those three reactions? Somebody else. Breaking a pi bond. Fair enough. Okay, so we could highlight that. The pi bond is broken. What else happened?
You form a chiral.
I don't want to draw chiral atoms, so I'm just going to say let's not worry about that. None of them are chirals, but that is fair. I do see it.
Hydrogen gained
Where's the hydrogen gained?
on the second position of the pylon. So the right part, rightmost
Did I
part.
really do that?
Yeah, you do.
Huh. Fair enough. It's a nice, easy way to place it. Whoops. The hydrogen is always placed to the right. Does it always have to be placed to the right? No, the structure could have been flipped over, so don't just run that assumption. That just happened to be how it was aligned. Can you describe that position to the right better than it's just to the right?
Less substituted.
It's on the less substituted. Where did our hydrogen go? The hydrogen went to the less substituted position. Right? Which means you should be able to tell me the other part of this.
It goes to the more substituted.
The
nucleophile is the more substituted.
The nucleophile went to the more substituted position. Right? Straightforward and simple. Why would it do that? Why would it do that?
Resonance.
Resonance. In all of those cases, what happens with our most stable resonance structure? We're putting the negative charge on the least substituted position because it's more stable there. We're putting the positive charge on the more substituted position, which makes it more stable. So our explanation is resonance. Right? How grand of a topic is resonance?
Awesome.
Like you're like, that is the epitome of all science. We should name whoever discovered resonance and attach their name to it. Right? Resonance is used so much that kind of like Lewis structures, no one really acknowledges how valuable they are. Right? Kind of like the Lewis definition of acids and bases. It is so broad and encompasses so much stuff that we don't want to use it. Right? Resonance is so broad of a topic that it applies all of those pieces out there that it can explain everything. So it's really, really cool. Do we acknowledge anybody who discovered resonance or first addressed that? No, not really. Do you know who we do acknowledge? This dude called Markovnikov. Why? Because when he ran the reaction, he saw that hydrogen went to the less substituted. Why? I don't know, it just does. Okay? We name these reactions as Markovnikov reactions, that the hydrogen went to the the less substituted position. Okay? There's a little mnemonic that can come with this. The rich get richer. If you count hydrogen as money, the more hydrogens you have, the more likely hydrogen is going to be put there. Right? And so students will memorize that mnemonic device, if it's mnemonic, whatever it is, and say, okay, great, this is a Markovnikov reaction. And I would argue that was a complete and utter waste of time. Why did those reactions happen the way they did? Resonance. Should you already know resonance like the back of your hand? Yes. Okay? So by telling you this mnemonic device, you're like, oh, I don't need to learn resonance. No, you just have to memorize more crap. How many of you are done memorizing? Right, there you go. That was nice. A little, I don't want to really be out there. Okay? If you want to memorize, by all means, you can deal with all the video, every freaking organic chemistry video out there. Go, oh, Markovnikov and anti-Markovnikov. And the reason we give Markovnikov credit is not because his observation is phenomenal. It's horrendously, moronically stupid when you consider that we understand electrons and protons and resonance. Okay? It is a trivial observation. So why do we give him so much credit?
Back then we didn't have great technology.
He discovered it before we knew about the electrons, the existence of electrons and protons. Okay? So yes, I give him credit for that. He made a phenomenal discovery when we didn't know better. Okay? How many of you people know who invented the wheel? Okay? So if we don't bother to memorize the name of the discoverer for the wheel, why do we need to bother to stamp some famous Russian dude's name on this? I don't have anything against Russians. They're cool. They did lots of cool stuff in OChem. Okay? But we should be acknowledging the chemistry, because the chemistry that drives these reactions is the exact same as the chemistry that drives all of our other electrophilic additions. There is no difference. And if you spend the time to come up with a way to differentiate them from each other, you're only screwing yourself over and making yourself memorize more. Look for their commonalities in the reactions of the electrons and protons, not in the differences of some stupid arbitrary name. Okay? So, that said, we'll go ahead and stop.